don't know the background. You know the background. Howdy. We're very happy, fortunate today to have Professor Eugenia Etkina, the chairwoman of the Department of Education, or Graduate School of Education. See, we had too much fun drinking coffee and not, talking about her background. But an expert in physics education. Highly recommended by a friend of mine who's a professor at Rutgers. We chatted through Skype a while back about her views on teaching, and prompted by Jairo's committee. And so we were very fortunate that she's coming to UT tomorrow, so we were able to snag her on the way there. She's going to tell us about her perspectives on ISLE, I-S-L-E. Thank you for coming.
Thank you. Thank you. My educational background, I'm a physics teacher, trained in Moscow State Pedagogical University, and I taught physics in middle school and high school for a long time in Russia, for 13 years before I came to the physics. Yes. Yes, I actually taught in a specialized math school, and all my students were 10 times smarter than I was, which was sometimes very frustrating. Extremely gifted students. And then I came and I taught physics in the physics department for a few years, and then started as an assistant professor in the Graduate School of Education in '97. It was a long time ago. So my major, the responsibility for whatever I do is prepare high school physics teachers. Rutgers has one of the biggest in the country programs in physics teacher preparation. It's in the Graduate School of Education. And I also work with people in the physics department reforming their courses, physics and astronomy courses, and I work with a few astronomy professors who some of you know too, and we're running research in their courses too. And I came today because Lucas was asking me about some approaches to reforms, and I know that you are looking to reform your undergraduate education. And I will offer you my perspective. It's personal. I am not claiming that this is the way to do it, but I just want to offer you an opinion that is based on what we know, how human brain works and how people learn. And what I'd like us to start with is that you read this lab handout. This is algebra-based course, and the students who are doing this lab, they learn DC circuits, they learn magnetism, but they have not seen electromagnetic induction at all.
I already read it. That's what you feel.
Oh, wonderful, wonderful. No, this is algebra-based non-physics majors. And these are not even pre-meds. This is the level below pre-meds. These are those who are not going to medical school. Exercise science, ecology, vets, not those who need to get an A in every course. When you finish reading, just look at me so I can see that you're done.
How long do they have to do this?
This is a 3-hour lab. Mm-hmm. And they write their write-ups, reports in the lab and hand them in. Yes, and in a very special way, and I'll show the way. Yes. Yes. Mm-hmm. They work in groups of 3 or 4, And they also have whiteboards, and at the end they put their results on the whiteboard, and they have a kind of a symposium. And they also can visit other groups and ask them questions, depending on the lab. But it's a very cooperative, collaborative exercise. Okay, so I see most of the eyes. So do you notice anything interesting about this lab? There's no drawing. Okay.
All words.
All words. Okay.
Not prescriptive.
Not prescriptive. What else?
States what they're going to learn ahead of
Right. What else? Does
significant amount of inquiry-driven strategy.
Does it tell them what to do? No. Does it tell them the theory? No. And what do you think happens when they start the first experiment? Panic. Yes. Complete panic. How do you do it? There's no battery. How do you get a current in this coil, right? No, this is actually lab 5 in the second semester. They don't expect any instructions. They expect them, and I will show you the timelines, how long it takes for them to get used to no instructions. About 5 to 7 weeks in the first semester. This is the second semester, so they're not expecting instructions, but they still panic. There's a panic at the beginning of almost every lab. Like, we haven't done it in lecture. And then one of them accidentally moves the magnet in a particular spot. Oh, we got the current. They say, what did you do? And they cannot repeat it. And then they start moving, and then they start going to different groups. Like, oh, you have to move it. You have to move it in a particular way. And so they all, after like 30 minutes, they're all convinced you need to have movement, right? And then come testing experiments. They understand that a coil with the current is like a magnet. So when you ask them what will happen if you move one coil with respect to the other, they predict correctly that there will be current. But then the next question is, what if you don't move the coils, you just open and close the switch? And then some of them who already connected the movement to changing magnetic field say there will be current. And we say, no, you can't say there will be current because you need to base your prediction on your rule. And the rule was the movement causes current. And disappointingly, they said then there should be no current. And many of them think there should be no current because there's no movement. And then they do the experiment, and the current is there. Everybody's cool because they rejected their rule, and now they have to modify it, and they're used to it. And so at the end, they leave the lab with the understanding that changing magnetic field produces current in a coil. And they have another experiment in which they investigate the magnitude of induced current. They have different coils, and they, figure out they need to move the magnet slower and faster. But it all happens accidentally, because when they are moving the magnet, they see the faster they move it, the greater the current, and so on and so forth. And then in the end, there are reflection questions, as you can see, right, that make them connect what they do to the content, to the process, and to their future life. And these types of questions we have in every lab. So they come to lecture. After this lab, they come to lecture with 200 people. This is a 200-student course. And this is where they discuss other things. And in a different version of the lab, they actually discover Lenz's law, too. Yes? That's a very good point. However, here, even if they know the answers, it doesn't help them very much because they need to build the circuit, they need to actually get it to work, and usually, you will not believe it. Even if they had a physics course, it does not affect what they do here because whatever they learned was so out of context and out of the connection. Well, believe it or not, we have almost 10 years of experience, and this was never a problem. Well, you will not believe how uniformly ignorant they actually are, even if they are the physics majors. Yes. But we will not go into that discussion right now, okay? So you're sitting here thinking, okay, what if we don't start in a lab, right? What if we don't have the lab coordinated with the course? How can you achieve the same idea? You can actually do it in lecture, and I will show you, a very similar process. You let your students observe the experiments, and you can do them live with a, telecamera that they can see the readings, or you can show the videos, and then you ask them, after observing all these experiments done systematically, when is current induced in a coil that is not connected to a battery? And after observing this sequence of experience, they talk to each other in groups. You can give them clickers to choose the answers from multiple choice list if you want, or you can let them call out from their seats, and you have a discussion about what conditions they think are necessary. And you set them up in a way, doing only motion, so they get convinced that the movement is necessary. And then you play the same game when after they came up with the rule, you ask them to make a prediction using this rule of the outcome of a different experiment. And in this experiment, it's the same as in the lab. They make a prediction what will happen if you have two coils and you change the current in one coil, what will happen in the other coil. And according to the rule that says it's the movement that produces induced current, the answer should be nothing. And then they observe the experiment. They see that there's something. They have to modify the rule. And by that time, it's the second semester, they are fine with rejecting the ideas, with testing them experimentally. In many cases, they have to design their own experiment to test the ideas that they invented. And the process continues for every concept twice, qualitatively and quantitatively. In the labs, they also collect data and find patterns and test and do pretty much the same thing. Looks complicated, but it's not really complicated. That's exactly what they just did in the lab. So we start with some very simple experiments. We call them observational experiments. We don't ask for any predictions before them. Students collect data. Can be qualitative, like in this lab, or quantitative. They work together, or they observe the experiments shown to them without explanations, and they need to look for patterns. And after they identify the patterns, working in groups, they put them on the whiteboards in the lab, or they call out, sitting in a large room meeting. We don't even call them lectures. We call them large room meetings. They come up with an explanation if possible, or mechanism, or some kind of a hypothesis, what could be happening, or a mathematical relation. And then what they do, they have to either design themselves, or you give them a new experiment that looks different, and they need to use whatever they came up with to make a prediction. And of course, when we're making predictions, we are assuming something that we don't even know that we're making those assumptions. These are the things that kill us at the end. But you make this prediction, and then what happens is that if the outcome matches what you predicted, if the answer is yes, it matches, it's not really good, because you need to do it again and again and again until you say, okay, I give up, cannot disprove it, I'm going to apply it. And then you go into doing application experiments. And this is a third kind of an experiment that you did not see in this lab, when students actually need to build something using the ideas that they tested and failed to reject. And if the outcome says no, like here, that they used the rule that the movement of the magnet produces current in a coil connected to a galvanometer, and then they see that no movement also produces current, so they cannot make a prediction that matches the outcome based on the idea. They need to revise, and here they come up with a different hypothesis, that it's the change in magnetic field. And sometimes they examine the assumptions, that they assumed something that wasn't true. And sometimes they say, we cannot come up with anything, we need to collect more data. So this is basically what you do when you're applying for a grant. You say, okay, somebody collected the data, we have this idea how to explain it, now we need to build a machine to test it. Or you say, we cannot say why this thing is happening, we need to collect more data before we can proceed to explanations. Yes?
Is the motivation here to give them mind is confused by the theory that is the physics?
Let me just hold on and not answer your question. Okay? Because you will see when the answer comes to your question. But it is, I would say, it's the most fundamental question of education. The question that you just asked. When is the place of concrete experience? So, this lab is 3 hours. So we have 2 55-minute large room meetings. We have 1 3-hour lab and 1 80-minute recitation per week. It's a 4-credit course. Lab is fully integrated. The lab basically drives the course. But it doesn't need to do it. You can actually achieve the same goals without the lab if you have lecture or large room meeting following the same principles. And so what are the principles? The students construct concepts where they attempt to explain very simple experiments. You choose these experiments. They cannot be flashy. They cannot be sexy. They really need to be very simple so pattern emerges easily. So the experiments now play a different role. They either experiments that help you build a model or an explanation, or they're the experiments that help you test the model, or they're experiments where you apply multiple models, but they are never verification experiments or illustration experiment, or we do not show something to show how what it is. Basically, they do not come after you provided an explanation. You can see it in this lab, but another thing that we do very seriously is representations. And representations means they need to draw a picture themselves, so you notice there is no picture. However, when they hand in their write-up and there is no picture of what they did, they will never get a good grade. Not only pictures, but these are graphs and motion diagrams, force diagrams, energy bar chart, momentum bar charts, Bernoulli bar charts. We have a whole suite of different representations that bridge the gap between words and mathematics. New ideas have to be tested experimentally. You can come up with any explanation, with any idea. Any idea is good as long as it is experimentally testable, and if it is rejected, it's even better. Simple language. We do not introduce any vocabulary before students come up with an idea. We do not tell them what it is called. After they construct the meaning, then we say, well, and this is called momentum. And the last very important thing, that we do not confront students' ideas that they bring to class, because they're all very productive ideas that come from everyday experience. We try to build on them. And again, all these strategies are based on what we know about how our brain works. So experiment and reasoning are sources of authority. Not the textbook, not some kind of a person telling them what it is, but experience and their own reasoning. And of course, we help them. It's not that they're inventing everything from scratch, right? The teacher is guiding, and in education, there's a very good term for this. It's called scaffolding. You know, when you're building a building, right, you have these scaffolds, and you slowly remove them. And that's what education should be about, is very scaffolding. So why do we do it this way? Isn't it much faster to tell them what electromagnetic induction is and then let them practice problems or, discuss some situations? And in order to answer this question, like, why do you need to start with concrete? That's when I ask you, like, what is learning? If I asked you a question, what is learning? What would you say? What happens when you learn something? Okay. Yes?
My students would say that you memorize a small fact so that you can say it back at the time of a test. And I tell them that's the Jeopardy mode, and we don't want to do that.
Right. But I'm asking you a slightly different question. When somebody learns something, when you learn something, what happens actually? Right. And this is a crucial answer to this question. It is a physical process that happens in the brain of the learner. And you would say, duh, we all know that. No, we don't. Because if we knew that, then when we're planning what is going to happen in class, we would think about the learner, not about the teacher. Because what the teacher does is basically, I would exaggerate a little bit, irrelevant. Because this is what happens in the teacher's brain. What we need to worry is what happens in the learner's brain. And what happens in the learner's brain is a very, very tricky process. Not only do we need to activate something that is already there, we need to create a signal that will connect the new idea to what is already there. We need to make the path so strong that next time when we ask the question, this path is activated. And there are billions of paths to the same piece of information, to the same neuron connection in the brain where that piece of information is stored. So it's incredibly, incredibly complicated process. So how does it happen? There's a wonderful book, The Art of Changing the Brain, written by a biology professor. Very, very simple. Reads like, love story, a novel. You cannot put it down. It's about how to change somebody's brain. And learning is changing the brain, is the physical change in the brain. So how does the brain work? And Zell shows a very interesting brain cycle. So imagine you walk into a dark room. We turn the lights off in this auditorium. It's perfect, right? Absolutely dark, and you see a yellow spot flickering a little bit. Can you visualize it? So you go carefully and you do this, right? Why would you do that? Yes, because you walk in, you're not expecting anything. You see this yellow spot, and your brain, this is your concrete experience, and you start reflecting, yellow, flickering. What could it be? Well, looks like a candle, right? If it's like a candle and I stretch my finger, I'll get burned, so you do this, you don't do that, right? Also, you're standing at the entrance to the airport, and a car comes, and there's a guy, you saw him on Skype, but you're not exactly sure, and you say, Lucas? You don't say, hi, Lucas. You say, Lucas? In case, he's not Lucas. You won't be that embarrassed. So that very soft question is your active testing. And this is the brain cycle. For any idea to be formed in your brain, you need to have some concrete experience. You need to connect this idea to what you already know. You need to think about it, and you need to actively test it. And if you think about the brain, then the concrete experience goes here. This is our sensory input. The reflective observation searches in the middle of your brain. This is where your abstract thinking is, closer to the front. Then your testing, your prediction is formed in the frontal lobe. And then you have to do the active testing, which involves the motor function. And the motor function is any kind of movement. You can do an experiment. You can move your tongue, actually. Speaking is active testing. You can write. As long as you're writing, you're moving. You can get up and think. That's why I bet if I go into a hallway during the day, I'll see many of you pacing, because you have to move when you're thinking. So all these parts of the brain have to be working together in order for learning to happen. And if you think about students sitting in lecture and listening to you, if they're just listening, have is the signal going into the back of their brain. If you're not making them go back and forth and physically move some parts of their bodies, learning is not happening. And they can theoretically receive all the signals. So the people who have damaged front lobes in, let's say, in a car accident, if you have bleeding in the frontal part of your brain, you can hear, you can see, but you don't know what you see. Yes?
I get the picture. Is the essential nature of the explicitly motor activity component on this test circle, is that authenticated that literally even abstract learning cannot occur without that?
Well, what is abstract learning? Well, in order to, and that's why research shows that students learn very little, right? If you're familiar with the results of physics, yes?
I can think of a good example where active testing really isn't possible. You go outside on a clear night and you see a light in the sky, and your brain tries to interpret what you're looking at, but you could be way off. When my father sees a bright star or a planet in the sky, his eyes and his brain see the International Space Station. It has, solar wings and stuff like that, and it's not there.
Right. That is perfectly fine. Because what he is doing is he has concrete experience, reflective observation, and the abstract hypothesis, right? So he doesn't know, forget about what we know. Like, he wouldn't know that the station is there. However, what he can do, he can talk to an astronomer about it.
And I tell him, no, that is the star Sirius. And I can tell he's in conflict because he goes, no, it isn't. It moves across the sky. I said, yes, but very slowly, not as fast as the space station.
Right. And so he's actively testing your ideas with you. But he needs to talk to you about it. So if he doesn't talk to you about it, he is not going to learn. And so what I'm trying to say is that when you want somebody to learn something, you need to think about what concrete experience this person will have, how this person will connect to this concrete experience, what she or he already knows, and how the person will test new ideas, these abstract hypotheses that appeared. And that might seem very daunting, but if you look at the Isle cycle circle that I showed, that when you design experiments and you collect data, that's your concrete experience, right? When students see something, but if they stop there, then that's the end. If you don't ask them what they saw and why it could be happening and how to test it or how it is happening, then it stops there. So the reflective observation is when they connect what they see to what they already know. And this is where we need to give them tools for analysis, for searching. And this is where all these representations come into play, right? And when they hypothesize, that's when they devise an explanation. This is when we need to help them with analogical modeling. And basically everything that we do in physics, it's analogical modeling, in a way. And here, when they're testing an explanation, that's an active testing. But it's only one way of testing. Actually talking in a group about it is also testing. Acting out a graph, a position versus time graph, or the motion of electrons and holes in a semiconductor, acting out, with the peers moving between the chairs, is a way of active testing, as long as there's some movement involved. And people are trying to connect ideas to each other. I'm going to show a picture right now. And those, yes?
The question asked a few moments ago, not by me, but it's one I would have asked if you had asked it first, is what you're saying says that our experience here today is wasting all of our time. We're not doing any physical action.
Not necessarily. Not necessarily.
I think I'm getting something from what you're saying because I'm doing the active testing up here.
Because
I'm thinking against my experience and comparing what you're saying. Why do students have to be doing something physical any more than I do? I'm getting it without being physical. Why can't they?
you know what? You needed to talk to me. And talking is testing too.
Well,
You
needed to talk to you because I disagree with you.
and when you leave, you'll be surprised how you will remember exactly what you told me. A lot of things that happened today you will forget, but you will not forget our conversation. And that is a very important part. As I yes.
Yeah, the question I have is exploratory learning, it's obviously a no-brainer, but it takes time. Like in a certain amount of hours that you have, it may not be feasible all the time. I mean, for kids, that is the best way. But I think I agree with a lot of people. We do thought experiments. We don't need actual experiments to do the active testing.
I did not say, or maybe I did, and I apologize, that active testing involves doing experiments. Active testing involves motor function. Motor function can be writing. Motor function can be drawing. Motor function can be talking, can be getting up, moving. Doing experiments is just one. But if you do not involve any kind of movement in learning, if you're just sitting here, you walk out of this room, you forget it. How many Yes, it is a little bit. The more you do it, the more different physical activities you do, motor function involved, the better it is. But just copying is not going to do it. You need to be writing your own ideas. Copying from the board is motor function, but it's not the active testing of your ideas. So when you ask your students to write their predictions and hand you small pieces of paper or write a reflection at the end of the lecture, what they think they understood and what was difficult, that is their active testing. But when they copy the notes from the board or the PowerPoint is not. So I would ask people who speak Russian, I know they may say anything, okay? So if you look at this, right, this is just a set of lines, straight lines, some ovals, some squiggles, right? And that's what you write on the board when you write a definition for something, right? And students look at it and say, yeah, some lines there, or some sound waves when, a professor is talking, sometimes facing the board for a long time. But if you show this, everybody will know what it is. And then, after a person has an image, then you can give it a name. It turns out that our brain remembers the information, it reads the information much better if it is stored as images. We don't store these wiggly lines. We store images. And so when students are learning, if you do not help them to have an image of something, if you start with words or with equations, which is even worse than words, these are abstract representations, they cannot find them in their brain. They're not sticking out there. So image formation has to precede words. And this is the second book that this guy wrote that just came out last year. The first one is The Art of Changing the Brain, and the second, From Brain to Mind. They're all on Amazon, very cheap. The first one is much easier to read. The second one is difficult to read, but very interesting. And so if you look at this cycle again, then you can see where the images come, right? So you want your students to have as many images, as many different images of the same thing as possible. So when you ask a question or when they need to find an answer, they can find these images. Search for an image. Yes, graph counts, but one graph doesn't count. Many counts if you connect the graph to the motion diagram. If you connect the graph to the actual movement, that would be even better. The bigger the image, the better.
But then I'd say, well, was it before or after World War II? By asking specific questions, jumping back and forth, she was able to actually end up with a day and a year. And it wasn't an image, it was a relationship.
Right. I didn't put it here, but that's exactly what Zal writes in his book, that the information is retrievable much better if you know when and where. And so how this piece of information relates to other pieces of information, where it belongs. So any kind of classification that students have helps them retrieve the information. So that's absolutely true. But there's another aspect of learning, which comes from cognitive science. Turns out And if you think about, even you think about physicists or biologists or whatever, how they work. If you observe a research group, and there were many science educators who spent months and months observing physicists doing research to find out when the discoveries happen. Turns out they happen during the group meetings usually. You do something and you find something, you get together with people, you discuss it with them, and somebody adds an idea and somebody poses a question, and you talk, and eventually a new idea emerges. Because learning is a social process. And if you think about the brain, you understand why learning has to be a social process. Because when you work with other people, you talk. You might get up, you might walk. You write something. You move. And so engaging students in working together, helping them activate each other's networks, is helping them learn.
And is that why most of our scientific progress at the meeting comes over coffee, lunch, and dinner?
Yes. And think about it. If I give you any problem, if I ask you to estimate something, and we're sitting in a coffee shop, what do you do first?
Get a piece of paper.
Yes, you get a napkin. So because, and you get a napkin not to write an equation, you get a napkin to draw a picture. And if you ask a question or give a problem to a student, they usually, want to look for an equation. In many ways, yes. But Facebook does not allow you for a lot of active testing and concrete experiences. But a lot of things happen on Facebook, and you'll be surprised how much work happens on Facebook. My students now are doing student teaching. They are working as teachers for a semester in different schools separated by, 30, 40 miles. And they have their own Facebook group, and they talk there all the time solving problems. So social media are a very, very good learning tool. I'm not saying it is the tool, but adding any kind of a discussion, an opportunity for discussion enhances learning experiences. Absolutely, you're right. So now, if we agree that we have some ideas of how people learn, the next question is, what do we want them to learn? And I'll ask this question more directly. What are the goals? So imagine you have a semester or 2 semesters, right, of general physics, or you have quantum mechanics or whatever, right? And you are planning your course. So the first thing that you do, of course, you say, okay, what do I want my students to leave this course with compared to what they came with, right? You start with setting the goals. Well, maybe there's something wrong the way we do it that this happens, right? They don't hate literature, they don't hate history, but for some reason, they end up, and I agree with you completely, hating physics. When people ask me, what do you do? And I say, teach physics. They say, man, you must be smart, right?
A lot of the people in this room like science because there is a definite answer. And in literature, how do you figure out the right answer? Who's to say what's the right answer? I found that irritating.
Well, I actually would doubt that there is a right answer to every question that we pose. Because we choose, and I would exaggerate again, so you want to argue with me, ridiculously unreal questions. We do not ask real physics questions because real questions, it depends, what kind of surface you have, what kind of weather conditions you have. But we deliberately set unrealistic problems. They're not even problems, they're puzzles. So when we teach them, when there's one right answer, in your lab there isn't. But in the classroom it is. We're not teaching them physics. We're teaching them some other kind of a discipline. But it's not the physics that we do. But that's a different story. So if you were to answer this question, and I would pose it this question about introductory physics, because if you want to start reforms, you probably want to start with your introductory physics. Like, what is it that you want your students to learn? Or how do you want them to be different? And when I ask this question, I usually give people a lot of time to talk to each other, and then they make a list, and we discuss this list. I'm not going to do it with you now. I am going to show you what people usually tell me. Agree? Right? And they might say, critical thinking or something, but that becomes very vague. Right? But think about people who will take one physics course, who are not physics majors. How many physics majors do you have? Undergraduate physics majors? 150.
No, 300.
No, this is total per year.
We have an incoming class of 150.
Physics majors. Wow.
Yeah, but that's just 1 year.
Oh, okay. Okay, well, I say at Rutgers we have about 50, right? Yes. Oh, no, 1 year.
Yeah.
Right? Each year we have about 50. How many do we have who take physics courses? Thousands, right? So physics majors constitute a small portion, but I argue that everything that I say here is true for physics majors even more. But I'm not going to irritate you with this much. I'll just say, let's talk about non-physics majors first. So if you think about what the purpose of education is, right? The purpose of education should be to prepare people to be successful in the future, right? So what do they need to be successful in the 21st century? So some of them are taken from the surveys of physics majors. Some of them are taken from ABET standards. Some of them are taken from the documents that NRC, National Research Council, produced. I can put more, but the idea is that factual information and the block on an inclined plane, they just don't enter 21st century. Because the factual information can be obtained from Googling very quickly, and problems where there's one right answer, they just don't exist. And so if you're always looking for one right answer, then somebody should know it, then you don't need to innovate, you don't need to be creative, you're not ready for the 21st century, and that's why 60% of openings, of job openings, go unfilled. Not because, we don't have jobs, we do, we don't have people. So, should we rethink the goals? And to think the goals, I want you to go back to physics. So what is physics? If you think about it, what is it? It's not chemistry, yeah. Yes, and actually, it's actually a very good, it's a side comment, is when you want somebody to learn something, they need to learn what it is not as much as what it is. And we often focus on what it is, not on what it's not. So do you agree that there's a finite or defined body of knowledge that we call physics, right?
Well, it's so broad.
Right. But, you can write Schrödinger equation, you can write uncertainty principle, you can write Newton's laws, right? So this is, I would call, a body of knowledge. But that's not physics, right? Huh?
No, its ability to model a system with the simplest possible way which captures all features. Right?
Agree. It's a process. And that's what physicists do, right? That's what physics is about. So if you look at physics, then the process plays a major role in it. But if you think about learning physics, that process that you just described so eloquently is missing. Students don't have an opportunity to do it because we feed them with these models. So we give them the body of knowledge, totally missing the process. And of course, sometimes we do the process, but I'm just, painting a big picture. And this is kind of sad, right? And you're thinking, okay, well, they cannot learn the content, the body of knowledge, and now you want us to teach them the process. How are we going to do that? So let's think about what the process is. So what do physicists do when they do physics? Not only what you said, because to build a model, you need to model something, right? You need to have some information. And you need to have effective representations for this information so you can work with it, right? So they represent information in multiple ways. And that's why, Feynman diagrams made this breakthrough. And the Cartesian coordinate system made a breakthrough. A whole new field of physics is created every time a new representation is made, right? So all these things that physicists do, right? Actually, students can do too. Not necessarily using the complicated concepts, but on a simple level, they can do it. And in fact, if you have children or grandchildren, you will see that they do it very naturally. So I have a little grandson, and I came to visit him, and I had my finger taped with a Band-Aid, and he looks at it and asks, "What is it?" And I said, "It's a boo-boo." And then he finds a scratch on my arm and looks at me and says, "That's a boo-boo." And then he finds a bruise. "That's a bruise. This is pattern recognition." And then he starts looking at himself. So if grandma has boo-boos, he should have some too. So he created a model of what boo-boos are like, and he is testing whether he has them too. So we are programmed to do this process, is that when we come to school, somehow, teachers or whatever happens, not teachers, we, all of us, we kill that. Very successful. So, why should we focus on the process? Because the process has the elements that will make our students successful in the future. And another argument is that they can encounter this process many, many times. Every time they learn a new concept, they can go through the same process. So the process will be repeated many, many times. And it turns out that you need at least 6 exposures to the same idea in multiple contexts in order to be able to retrieve it from memory. At least 6, sometimes 8 or 9. And if they go through this process multiple times, then they will remember the process. And then when they face a problem in real world, they can use this process to solve the problem. So I suggest a completely different approach to physics. The body of knowledge is not the goal. It's a context. You can't learn the process in an empty room. You need to learn something, right? And luckily we have this something. We have Newton's laws, and we have kinematics and momentum and energy and electric field. We have all this. Let it be the context for developing the process skills. And this is exactly what IEL does. So you're sitting here and asking, yeah, but still, do they learn physics? And by physics, you think the content, right? So in order to clear the picture, I will say, does IEL work for the traditional goals? So do you know what Hake gain is? Okay, Hake gain is a measure of learning. And you should try it in your classes. Physics Education Research developed a few conceptual, very interesting multiple choice tests that assess basic understanding. And you'd be surprised how poorly your students will do on those tests, though the questions seem very, very simple. And the gain, the learning, is measured the following way. Let's say you have 30 questions, right? So a student can get 30 questions right. On the pre-test, the right number is, the number of right questions is 5, right? On a post-test, it is 30. So the gain is 1. Right? Because post minus pre is 25. Maximum post minus pre is 25. The answer is 1. And this is what we want. Right? What are the gains in traditionally taught courses? You teach mechanics. You give students force concept inventory, 30-item test, no mathematics whatsoever, questions simple as, you look at them and you will think the students will get insulted. What do you think the gains are? 0.2. 0.2 in traditionally taught classes independently of the instructor. You can be an award-winning professor. You can be a first-year teacher. You will not get above 0.2. They can be a little higher if you have brilliant students, like at Harvard. You can get to 0.25 probably, but you will not get to 0.3. In the reformed courses, they range from 0.2 all the way to 0.9. They strongly depend on the pretest score in reformed classes. If your students are very low, it's very difficult to have a high gain. But if they're Harvard students, then Eric Mazur gets 0.9 easily, 0.8, 0.9 easily. And before he switched to some kind of a reformed instruction that he does, he was around 0.2. That is a very good question. How do you track it? You can track it in the second course, but then they all disperse and because these are not physics majors. And there are people who track. Yes, yes. Yeah, you can have an outlier with a 0.9, but that's your average. So basically, they learn 20% of what you want them to learn. Some courses, that's the highest. Some courses 0.1, some courses 0. So our Hague gains are from 0.3 for new, unexperienced people, and for very, very low at-risk populations, those who start with the pretest of 5, all the way to 0.7. And we do not work with Harvard students, so all our students are Rutgers level students or Ohio State level students or high school students. My first-year teachers get 0.6 gain on FCI, teaching their first year in a high school. And their high school students start very low using these methods. There's another test, conceptual survey. Yes?
You need to say maybe a little bit more about what these tests are. Because if these are nice qualitative questions, I could teach those qualitative questions. I could get my score up too, but then when the engineers inherit my students the next year and find they can't do a problem, they're not happy.
Yeah, well, in fact, we did studies when we correlated the FCI performance with the problem-solving performance. It's a very high correlation.
Really?
Yes,
How
yes.
do students from a reformed class do on unreformed classes?
Good question. Here is the answer. So, here, that's what we did. So we did IEL at Rutgers, but before they had data for student performance on a bank of problems. And so the professor chose the questions for our students, and that's how they did. So they do fine. They're fine. They learn physics. And you'll say, well, you need to skip something. Yes, you do. You decide what you want to skip. But knowing deep in your heart that if you don't, they don't learn anything, then, And we even have a word for this. We say we covered. Covered. Right? Let's uncover something, right? So we want more than FCI. I'm going to show you 2 questions from our exams, like real questions. So you'll say, well, how do you assess whether they actually can think like physicists? right? So that's an example of an exam problem. Good question. Good question. We have 200 students. How do we grade those? Very interestingly, we do it. We have all the exams that have open-ended problems for 200 students. How we do it? We have TAs, right? And you have TAs probably, right? And TAs have their teaching load. So if you think of assessment as a part of teaching, not an add-on, then you factor into the teaching load the exam grading. So we thought of how we can minimize the grading of homeworks and labs and combine the office hours. So we have free time for exams. Exam grading is actually like a party. We bring food. Everybody gets a problem. If you grade 200 of the same problems, it's relatively fast. You can make it. But for this, you need to believe that your assessment should actually match your goals. So if your goal is to teach them to think, your assessment should be of their thinking, not of the facts. And this is difficult, but these are the things that you need to think about. Do you want to integrate labs? What kind of exams do you want to have? When will students read the textbook? When will they do this? When will they do that? And I don't know if I have time to actually do it. I'm on, I don't know, maybe 1/3 of my slide. Oh, only because you're interrupting me all the time. Yes, yes, yes.
So, I consider myself to be like, because I know this, right? And I would have hated this question on the exam. With all my guts, I would quit physics right away if I had such questions in my exam.
We have worse questions. We have a question. We have a question, for example, what's his name? Artem is saying heat rises. Why would he say this kind of thing? What is correct about it? What is incorrect about it? How would you... Heat rises. People say heat rises, right? We know it doesn't, but people say it. So when students hear it, we want them to be able to say why somebody would say that heat rises. What is correct in this statement? What is incorrect? And how to convince the person that heat actually does not rise. Right? This is another exam question. Here's one more. It's a long one. So they do a lab in which, you know Hot Wheels cars? Right? So they have a launcher, and they need to figure out the potential energy in the, basically they need to figure out what is the smallest setting on the launcher so the car makes the loop on the first try on the minimum setting. So it doesn't fall off, but it's not too fast. And for this, they need to figure out that they need to find the potential energy stored in the launcher. And they do experiments, and then they, test this car going, and so on and so forth. And so that's the problem. I want you to read it. So these are non-physics majors, and 70% of them never take physics before they come to college. A lot of them are seniors because they postpone taking physics till the last moment. They need it as a requirement for graduation, but they don't want to take it. So they have about 5 of those problems on the regular exam, which lasts 50 minutes, and they have 10 on the final. So when and how do students develop abilities to solve those problems and do it? And so one of the ways to do it is the lab drives the course. So it's in the lab students come up with ideas and test them. and they do not read the textbook before they come to class. So a lot of reformed methods are based on the fact that students read the textbook before they come to class. And then they come to class and they do, discussions and they answer questions with clickers. This leads to improved learning because they talk to each other. However, what it removes is the process of physics, because they get everything from authority, from the textbook. So it doesn't solve the problem of preparing them for the future. It just solves the problem of them being able to solve back of the chapter unrealistic problems that we don't even want them to solve. So you can teach them read the textbook, and our students read the textbook, but they read it after. And they read it because we give them a statement, and we ask them, why is this statement true? And they need to find out, the argument in the textbook, or come up with their own, but say where in the textbook the argument is meant, why the sentence is true. So they read it as a resource, not a source of authority, after they come up with ideas. And they design experiments in every lab, and this is an example of experiments. So some of them are observational, that they do before they do anything in a large room meeting. And some of them are testing experiments. And sometimes they test the ideas. Sometimes they test ideas that we know they have. For example, if you ask your students when they do, any kind of electrostatic experiments, why objects attract and repel, if you ever ask this question, you'll get the answer, because they're magnets. And they test this idea. They actually have to test whether charged objects are magnets. And they need to figure out how to do it. And this is an application experiment that they do. And then we also have, at the end of each semester, we have a pose your own question lab. We post on the website the pictures of equipment that they can use. They can pose any question, send their proposal. It's like you're writing a grant, right? You have this equipment in your lab and you want to answer this question. The TA reviews the question, and usually all of them get approved, and then they go and struggle in the middle of the lab. They realize that they messed up completely and they need to start all over, or they answer one question, a new question emerges. But it's their favorite lab. And you would say, how can they do it? Well, because we have the tools. We have what's called scientific abilities rubrics, and we also have the questions, the guiding questions you saw in the lab that help them to think about things. So the rubrics, we have a website with those rubrics. They describe these abilities that we want them to develop and help them evaluate their own write-ups. For example, imagine they have a lab in which they need to determine the specific heat of a rock. We give them a rock and we ask them determine specific heat of a rock. They know they need to do two different experiments, as different as they can, not repeat the same experiment. They need to repeat the same, but it won't be enough. And then they get two different answers. So should one be more than the other? Depending on, if you take a cold object, put it in hot water, you take a hot object, put it in cold water, or you warm them up together. Depending on this, your assumption that no energy is transferred to the environment leads to a larger or a smaller number. So they need to understand these assumptions, and they need to be able to validate them. And when they submit their lab report, there's a certain number of rubrics according to which they will be evaluated. They know those rubrics. They use them to self-evaluate themselves. And all the rubrics are written in the same way. The idea is more or less the same. So 3 is as perfect as we can expect. 2, a student writes relevant things with some minor omissions. 1, a student knows that she needs to write something but doesn't know what. And 1, the student doesn't do it at all. So when you tell them what they need to focus on, then they focus on it. And it takes some time, but they actually develop these abilities. I'll show you how long it takes. So that's an ability to evaluate uncertainty. And we do the weakest link rule. They learn to estimate what instrument or randomness gives them the biggest uncertainty. And you see it takes about 5 weeks for them to get to about 80% of being okay. So if you start at the beginning and they cannot do it, and you quit, they never learn. And this is another ability to identify assumptions. You can also see that about by lab 5, they get to the 80%. Evaluate the role of assumptions is a more difficult ability. See, it grows. It never reaches what we call saturation because content dependent is very difficult. So that's the most difficult ability that we found. And you almost never get to 80%. So students can do it. And I also have here, I'm going to stop right now, I have research that shows what they actually do in those labs compared to cookbook labs, traditional labs. I can show if you want me to. If not, it's not necessary. But the message is that you can change the goals of your courses. The students will be successful in traditional stuff. They will learn much more than in traditional courses, and they will have some idea what physics is, as opposed to what we teach them now. And I would say, I want to finish with a quote from my friend who came from Russia a few years ago to visit me, and I took her to Dunkin' Donuts. And she said, this is not coffee. This is some other kind of drink. I might even like it, but don't call it coffee. And that is sometimes what happens when we teach physics. We teach something, but it's not the physics that we do and love. And what I was trying to do, two things, is to share my understanding of how people learn anything and share my views of what kind of physics they can learn if we let them learn using the knowledge of how people learn. Oh man, that was complicated. Thank you.
Other questions? Do you have a metric for how students feel whether it's fun or not? Because I would say that one of the other things I'm going to teach in science is to sort of rephrase what Feynman said, that science is figuring stuff out and not proving yourself. But at the very end, I want them to have science be fun. So do you have a way of measuring that also? Because to me, that's one of the essences of what you were talking about little kids who are all constantly doing science experiments, because back then it's really cool and they don't get tested on at the end of the year. It's not as if their Christmas present is going to be dependent on whether they count them for boobs. So it's the testing process, which we still have in all these classes, we're not getting rid of, which strips a lot of fun out of doing science. And is there a way to measure fun?
Yes, there are surveys that measure motivation, and there are actually methods that improve motivation. And one of those methods you can see in the lab is that they need to connect what they're doing in the lab to their future work, so they see the purpose of it. Another way to improve motivation is to help them see that they're getting better. We're motivated to do things, in which we're getting better, right? And you're absolutely right that grading destroys fun. And how to compromise, it's difficult. But what we find is that at the beginning, our students, and a lot of them are juniors and seniors, they're very unhappy. It's like, what is that? We're doing something in the lab that we didn't do in lecture. Where's the instructions? You didn't give them us instructions. And they hate it. And then gradually, about 80% start loving it. And I will never forget one of the girls who said, I come into a lab knowing that what I see is impossible to do, and I know that when I leave, I will know how to do it. And that's the best part. And so I think that challenging them and giving them the sense of accomplishment can beat it. We also have learning assistants. I don't know if you know about this program that helps them with that. We have extensive help that helps. We have a recovery points approach. I can talk forever about what we do to help them with motivation. But we actually show them it's the learning that counts, and if they want to learn, we'll give them all the opportunities to learn, and the grade is not final. They can redo the labs, they can redo the homeworks, they can get all the points. And that's important, yes.
Just a quick question. They take the lab before the lecture at the meeting.
Mm-hmm. Sometimes. It all depends. Right. So when we started in courses that had 600 students, and it was impossible to have them all through the lab before a lecture. So we only did application experiments in labs. So they did these aisle cycles. They watched the videos. They watched the real experiments. They had this, couple discussions, and they click questions and multiple representation questions and everything. And they would come to a lab and solve problems based on what they did. The last type of experiments are application experiments, when you're putting many concepts together. So like determining the specific heat of a material is an application experiment. Determining the density of a floating object is this kind of an experiment. We have an experiment determine the coefficient of friction between your shoe and the carpet. So this is what they do after. So you can't, this is a variation. As I said, that's why I gave you the lab handout, but I also showed you the videos that mimic the experiments you can do in the lecture when they still do the same thing, only they don't touch stuff. Yes?
Maybe a long question, but I'm trying to formulate. It seems to me what you're saying, I think, is a great idea. Sounds like it works great for people who are not going to go on in physics. They're doing something else. They're going to be something else. But now we've got, in my view, we've got a broad scale of this. We've got one end, the physics majors, and you were prepared to sort of eliminate them. Then we have
No. I'm sorry. I'm going to interrupt you. No, I did not say we're prepared to. I said the physics majors needed the most. I said I have the data for non-physics majors. And I'll tell you why I do not have physics majors. Or maybe you will be 10 times more.
That's a different question. Let's not discuss that.
Yeah. So, sorry, I interrupted you. Yes.
I'm trying to think of this in an analogy with, let's say, music. Music has all sorts of wonderful overall ideas to it that physics does. And if you are just going to give a person a course who's not going to go on in it, but just wants to be a complete human being, they take physics or music appreciation. They hear lots of music. They get somebody talking about it. It's what you're advocating here. But
No.
if you want to become a musician,
No.
you practice scales, which is boring as hell, but it's something you need in your repertoire, so to speak, so you can proceed to the next step, which is to do something with it.
Let me comment on this first. It turns out that some of us, this is program parallel to physics, are mistaken. Most of us are physicists in spite of the system. Totally in spite of the education system. Now, what she has described very well is how we actually work in real life. Now, the students themselves, they never get exposed to any of that methodology of how we work. Now, what do we actually do all the time? Harmonic oscillator appears in every course. The student will hear it in one course, and then independently in another course. They never connect the two courses together. In Oregon State, for example, in this case, they actually perform, and they show that it works very well, where at the junior level, where we actually software engineering and STEM students introduce all the concepts. So you actually put all the content that you want to teach, all the content on little cards, and then reorganize it around paradigms that are connected. You don't miss anything. You cover everything. Sure, but the content. And it does work. Now, in this particular case,
I'm not
this is
arguing
exactly what she was doing.
I'm not arguing against all this stuff. I'm trying to sort of put it in a way which doesn't throw out the baby with the bathwater. That's what I see happening. I see if we concentrate entirely on the process, then we're concentrating on a musician having musical ability without being able to play properly.
But did I say it? Yeah.
You won't do scales in that class. Scales is something you do often in one-on-one with teachers. Not do that.
You wouldn't perform.
Not in that class.
No, but that's because you've done it already.
I think maybe I need to repeat what I said, that we use the normative knowledge as the context to think like a physicist. So you saw the problems that we give our students. If you go to this problem, this is your traditional problem, only much more complicated. This is your traditional problem, only much more complicated. So we do not water it down. In fact, it's much more complicated in terms of physics because they need to evaluate assumptions. They need to understand how uncertainties enter the data that we are collecting. And they are doing as well or better on the tests that are used to evaluate students all over the country. So we're not doing what you're saying at all. On the contrary, we are enriching what they do by engaging them in the processes that you are engaged in, by giving them an opportunity to have a taste of physics.
John, let me address one thing, though, which is important. The process that we are going to change, it's not going to be easy. It's not going to be just referring to the throwing away the baby with the bathwater. You're worried that, then sometimes a very good lecturer can really make this point, too. And something connecting concepts. It's not about just completely throwing away that. It never has been that case. It's about combining things. In the way that we feel comfortable with. It's not going to be the exact thing that Rutgers does. It's not going to be exactly what Illinois does. We need to figure out what works. But it certainly cannot be what we have been doing. Today I had a discussion with one faculty member that was painful on exactly the type of lecture you don't want to have.
I would see this as being, what is now a 2-semester introduction to physics, as being the 3rd semester. I think this would be great, whether it's the 1st or the 3rd, doesn't matter. But it's an add-on, which I think is excellent. But I don't see how, if I were trying to present that class teaching DNA, how I get in all of the concepts, and if I don't get all the concepts in, then our customer, the engineering department, had better be happy with what I'm leaving out.
This is where I think we need to engage. We are engaged. We're engaged, and we're actually with the engineer guys on what we're going to do. We're going to bring them all the time. Any process that we're in charge of doing it. Even if the physicists hate the questions, but at the same time, it's not so much about. The same thing. Discussion today that I had. The goal of this person was to go to as many examples as possible. This person went to 15 examples in less than an hour. Guess how many they actually understood? Now, content. Oh yeah, they covered a whole lot of content. That was it.
But you covered all of E&M in a semester.
Right. Now, what I want to say is that if you interview, you all saw the, the videos from Harvard graduation, right? Yes, and the fact that people cannot, light a bulb with a battery and a wire. I just read an interview with a senior engineering student with a 3.8 GPA who says, I'm an electrical engineer. I don't know what voltage is. I did a small project in an E&M course, 300 level at Rutgers, where students every week needed to write answers to a few questions. First, what did I learn this week? Second, what remained unclear? And third, if I were the professor, what questions would I ask to find out if my students understood the material? And so, and I coded the difficulty of the questions that they asked that they could not understand and the questions that they thought the professor would ask. And so what they did not understand, the questions were almost, brought me to tears. 4th week, what's electric field? And the questions that the professor would ask would be, this surface integrals and stuff. So that's what is happening. In terms of lectures, I want to add, is that you can think of lecture as an integrating experience. So all these concrete experiences and thinking and testing, they are kind of just disjointed in the student's head. And then they come to lecture, and this is when you provide an integration. And their eyes open up because there's something to connect. And this is called time for telling. So basically learning happens when first you innovate, you create a concept, you struggle, maybe you solve a problem, you try to solve a problem and you don't succeed, but your brain is kind of warmed up. And then when you hear the solution, then your brain makes the connections. But if you did not struggle before, if you don't have a question, if I tell you now how to do a rotation on my, right foot, you probably would not care and you would not learn. But if you spend an hour trying to do it, you would really pay attention to what I do. So that is the change that needs to happen in our education, that we provide answers when students have questions. But we usually give them answers when they don't have any questions.
I would pay that to the students, but I'm not a student. No. The question which I have, it's not a question, it's a comment. I think that the strategy should have been done in elementary, not intermediate high school. This is the perfect time for it. Come here to the university, thinking to give it substance. That's my dream.
So you don't deal with substance at your work, right? When you work in physics, you don't deal with substance. Right? There's no substance in it. I think that this method, it actually is much better for graduate physics courses. So they know where these equations came from. Because if you look at graduate courses, it is, math, problem, math, problem. So and if you read Max Born, he says that quantum mechanics is the most experimental part of physics. But our students never know where these equations came from.
What we described before, people remember images better than words for even equations, which is I'm completely against, because equation to me is a picture.
Yes. Yes. And how many of you?
It was developed before I went to university.
Yes.
For me, to describe a picture, I use a formula. That's
Right.
the same thing. It's just much shorter.
Right. And so people like you are very rare. In my 13 years of right. And so let's say 50 years ago, when few people took physics, or maybe 100 years ago, only those who were supposed to be physicists took physics, that would work. The methods that worked for you would work for everybody else. Now, so many people take physics who are not like you, that it's kind of strange to assume that they will all learn in the same way. And I know exactly what you're talking about. When I was teaching physics back in Moscow, and I was trying to make my students draw pictures when they read the problem, the first thing, tell me what you see. What's your image? Draw a picture. One of my students said, I see an equation. And I had 3 of these students in 13 years. Okay, so you're a very, very rare, very special person. Yes.
You've discussed these principles of learning in the context of teaching students. When we're presenting our research to our peers, is there something else different we should be doing?
Yes, probably you should help them with imagery. And you should help them connect to what they already know. And that's what happens. Some colloquia you go and you remember them, and some you go and you don't remember anything. And so some people intuitively follow these rules, and some people don't. But when you give an opportunity for your audience to discuss things, they will remember. Yes?
So in your characterization just a moment ago, where you talked about students struggling with
struggling potentiates the neurology of things so that the aha moment can make a connection.
Right.
Is there cognitive science that would deal with the correlation time that persists for the potentiation before it's lost?
That's a very, very good question. I don't think that these studies usually are done in a lab environment.